Hello everyone, nice to meet you all. I'm happy to announce that we are preparing for the second round of the Curious Today Partner Tomorrow event on October 27th, which is a cyber physical event. So you have the options of joining online or physical at SDU campus. The topic will be additive manufacturing. So we will review the 3D printing technologies and also different industrial applications. We will also discuss how additive manufacturing can be used in a collaborative way to increase the efficiency in the production. So see you on October 27th.
Hello everyone, and welcome to Curious Today Partner Tomorrow, the second round of the event this year. And I'm happy to here as a presenter. For those of you who don't know me, my name is Saeed. I'm head of the Industry 4.0 section. And the topic, as mentioned by Morten, is additive manufacturing. And that's the pointer. Okay, cool. Then my intention today here is to provide you a helicopter view about additive manufacturing and also a very brief applications. And then my colleagues later on, they will elaborate more about the new technology or new printing technology and also the applications. So I don't go into the details in my presentation. Here is the brief agenda. So I start with the introduction, why AM, and also main technology, a strategic focus area, also AM manufacturing readiness level, and our main application, challenges, and finally AM system integration. That this part will be covered by my colleague Sune, who is standing here, and then I will hand over the stage to him once I'm done with my presentation. Okay, cool. Yeah, this is a list of the existing technology, which is not something new to you. For example, thermodynamics, CFD simulation, mechanical design, material science, FEA, thermodynamics, and software developments. That is something that in the part manufacturing companies and in many other industries, the engineers, they are dealing on a daily basis. But we also have some emerging technology, and we call them Industry 4.0. And all these new emerging technology, they help to have a smarter production setup. For example, you can see a list of elements under the umbrella of Industry 4.0, like IoT, cybersecurity, augmented virtual reality, machine learning, big data analytics, location detection, cloud computing, mobile devices. But additive manufacturing, as you see, is the front runner here. So it's already have emerged to the existing technology. But in order to adopt additive manufacturing and industrialize additive manufacturing, we need system integration. And that's why my presentation today has two parts. I will elaborate about additive manufacturing, and soon my colleague will talk about system integration. Perfect. This brings us to the next slide, which is about why AM. Design for manufacturing and assembly versus design for additive manufacturing. So if you have this horizontal line, which represent time, and then we have the production. So, and also the vertical axis is the percentages. It could be a percentage of the design freedom or cost. No matter which manufacturing technology we are using, our knowledge over the time will be increased until end of the production. But then what differentiates us is the design freedom in traditional approach. So when we are taking the traditional approach, as you can see, our design freedom is actually significantly drops when we approach to the production zone. And consequently, the cost of the change also dramatically goes up when we enter to the production phase. And here, additive manufacturing shows its value. As you can see here, this design freedom utilizing by AM. So this means that if we use this, if you look at this solid green line, this is the design freedom by AM. And just before the production, you can see we have almost 100% design freedom for AM. And consequently, again, the cost of the change, if it is needed just before the production, is really less. So it's under 10%. So, and that is why additive manufacturing is interesting. Okay, then let's look at the different additive manufacturing technology that we have. We can classify additive manufacturing in two main categories: direct 3D printing and indirect 3D printing. And direct 3D printing, you can see we have 7 common printing technology: wet photopolymerization, material extrusion, material jetting, powder bed fusion, and so on. And you can see the advantage of direct 3D printing is flexibility and freedom of design, lower startup cost, and tooling investment. And indirect 3D printing is divided to 2 sections: soft tooling and freeform injection molding. And soft tooling is we 3D print the mold, and then we can actually inject the material. And you can see the list of advantage here: short lead time and low cost of design, reduced production lead time, and process predictability and repeatability. And about freeform injection molding, one of our co-hosts, Lasse Ståhl, the CEO of Additive, will elaborate more on that. But as you can see here, if you look at the green area here, here is the main advantage of freeform injection molding. Freeform injection molding can combine the design freedom of AM with the material versatility, material diversity of injection molding for short series production. So design freedom, unlimited material access, and versatility and scalability of injection molding. That is the main advantage of freeform injection molding. Okay, AM strategic focus area. This is not something new to you. It can be used for fast prototyping, agile manufacturing, and design optimization. So again, I don't go into the details. I just skip this slide as it is, and I go to the next. Oh, and this is interesting slide. Who is the most benefiting from AM? So you can see aerospace, automotive, medical, and also the company who was dealing with injection molding. They are the most benefiting companies from AM. And this is what you see on the right-hand side. This is the technology readiness level, starting from 1 goes to 10. And 1 means basic implementation, and 10 is the full rate production. And as you can see in the aerospace, tooling, and medical, they are the most benefiting. And the reason behind that is very obvious. They are highly specialized. They produce highly specialized part and also low volume production. Yeah, the challenges, very briefly, there are 4 main challenges. Again, it is some of you are familiar with these challenges, but I go through it very briefly. Part identification and process identification, design for AM, functionality and reliability, test, material qualification, and testing. It is very important to actually identify the most suitable component to be manufactured by AM. And also you need to have a good understanding about the AM processes in order to have a successful launch of the product. And also finally, you need to be able to develop the business case for that. And then when it comes to the design, you need to improve the current design or develop a new concept with a focus on improving the current solution, differentiate your new product compared to the existing product in the portfolio, design optimization, and also manufacturing constraint. And then when it comes to the functionality and reliability test, this is extremely important because you need to design and manufacture the test device for functional testing. And also you need to do the lifetime test, or some companies, they call it accelerated test. And also you need to make sure about the dimensional stability and strength investigation on the real working condition. And then finally, material qualification and testing. You need to qualify the material and not just rely on the data sheet published by the material provider. So you need to come up with your own test protocol depending on your application, and then which validation and verification tools is needed for you. And then finally, you need to design and manufacture the test device and issue or publish the material certification together with your parts manufactured by AM. Okay, I think this brings us back to the first slide. So how to industrialize the additive manufacturing, especially in the big organization. So it is not just a matter of buying some printers. We need a system integration to fully benefit from additive manufacturing. And this topic will be elaborated by Sune, who is standing here. So Sune, the stage is yours, and then you can go ahead.
Yes. So hi, my name is Sune, and I'm working as a PhD student at the SDU Software Engineering. My research field is about investigating software architectures in relation to Industry 4.0. Currently, we are working on an IoT software project for Industry 4.0. sponsored by Infinite in close collaboration with the industry partners. One of the focus areas has been to design a general open source software platform around advanced robotics and automation solution, facilitating communication and coordination among machines. In this presentation, I will tell about how software platform and how it relates to additive manufacturing. Yeah, okay, so this should be the first slide. The first slide, yes. So the image above emphasizes a highly integratable software platform, also stated as the information backbone, facilitating communication, data collection, and coordination among software and the machines and services. Also note that the integration to the enterprise resource system, which triggers the production order sequence. We analyzed software qualities such as reconfigurability, supporting the I4 vision of having a flexible production with increasing demands to handle changing requirements. Furthermore, we have investigated interoperability between machines and services and how ontologies are used to express semantic knowledge about available machine resources in the production. In general, solving system integration between software systems in a heterogeneous setting is a prerequisite for supporting areas such as big data, machine learning, and simulation. So basically, we are architecting and constructing systems around robotic and automation solutions, but this could as well include integration to additive manufacturing. So in the image above extends the idea about having a software platform facilitating communication and coordination of a production line containing additive manufacturing is not that far away. We have replaced robotic solutions with additive manufacturing solution to illustrate the software platform's flexibility. Instead of communicating with robotic solution, we are now communicating with a 3D printer, constructing products originating from plastic, metal, rubber, and ceramic material. Also, we added the ability to facilitate communication and coordination of the printer components cleaning process, involving the transportation of a printer components to the cleaning machine. In conclusion, if anyone, both from industry or academia, have questions, wants to collaborate, or do knowledge sharing, please reach out. We are open to new projects. Yes.
Okay. Thank you very much, Suna.
Yes.
About the system integration. Can you hear me? I hope, yeah, it's fine. Okay, good. Thank you very much for your attention. So I think we have 2 minutes, if I'm correct, for some possible questions. So please go ahead if there is anyone has some questions.
Yes, we have a question from Kelvin. Kelvin, yeah? Please go ahead.
Thank you very much. I'm Kelvin Nygaard from the company Move2X. We do work with all of these new technologies. So one thing, Saeed, is working with this Freeform injection system. Can you use recyclable plastics in this system? Yeah. Or is it only resins that can be used?
No, with this Freeform injection molding, basically you can process all the feedstock that can be used in the traditional injection molding. And that is the beauty of Freeform injection molding. And one of the focus area today is about how to process the recyclable material. And it can be actually processed with the traditional injection molding. But when it comes to the short series production, then it's a huge problem because of the high startup cost and also tooling design and manufacturing for the traditional injection molding. And that's how the recyclable material can be definitely processed with Freeform injection molding.
Yeah. Yes, we have another question from Marcel. Marcel, please go ahead.
We cannot hear you, Marcel.
Do I go through?
Yes.
All right. Okay. It was the four parts that you said benefit the most. What about electronics?
You mean how the electronics benefit from 3D printing?
Yeah, I'm thinking if you think Samsung or the like, I'm thinking in companies such as Nanofabrica producing micro 3D printing.
Yeah, that is something I think the electronic device or PCB manufacturer, they benefit from AM in two general ways. By manufacturing of some jigs and dedicated jigs and fixtures in the production line. And also nowadays it is possible to 3D print the copper. So this means that if you have a prototype and you need to 3D print a circuit board, for example, in copper, then I think you can also 3D print the copper. I haven't seen any prototype, but I have heard that it is possible to actually produce the circuit board manufactured in copper material. Yeah, I think we don't have any more time. So then if you have any other questions, you're welcome to post it on the chat box, and Sarah will collect all the information, and I would be more than happy to come back to you with I do my best to answer your questions. Okay, thank you very much and have a nice day, guys.
Thank you, thank you, Said.
Yep.
We will move on to Henrik Bligfeld.
Hi everyone, my name is Henrik Bligfeld. I come from the Operation Management section at SDU. And I will be here at Curious today, Partner tomorrow, to present some of our results and research about additive manufacturing in operations and manufacturing. We see a lot of potential about how to work with this multi-purpose technology, both within innovation, rapid prototyping, within tools and fixtures, but also in products. And we have a lot of different things that we can both show, but also discuss with you. So looking forward to see you. Now I'm on. Thank you very much. I have the delight of having the opportunity to tell you a little bit about how to adopt AM in manufacturing. So that's also the reason why we are in our manufacturing facility. My name is, as I said, Henrik Bligfeld. I'm coming from the Engineering Operation Management section here at SDU. At the same time, I also have the coordination role for additive manufacturing activities here. So not that I'm the expert, but I'm trying to coordinate our projects, our resources, and in general what we are doing here, especially the knowledge. And I can see from the participants list that we have someone here with a lot of knowledge, but we also have some who has almost nothing. So that's actually also the whole purpose about this. So when we talk about knowledge, and this is very, very old school, we have additive manufacturing as a really multi-purpose technology. So if we try to hold this up, I know Said also had something about this. We have the 3D print technology, which is divided into either the R&D innovation side, with the rapid prototyping. I will not go that much into that. But then we have the manufacturing side, either as direct manufacturing in products, and then or direct tooling, where we can support our manufacturing. And this is where we really see some important and interesting potential. And then what is then really important about knowledge is that this is actually the complexity of additive manufacturing, because you should know something about both the technology itself. So he talked about that. There are a number of technologies, but you also need to know something about design. You need to know something about materials, and then you also need to know something about the post-processing and also how to ensure quality. And all this in combination is actually a relatively large task. And if you move from rapid prototyping over direct tooling to end components and products, you will have an increase in complexity in understanding all this and do it in a combination. So, and then what do we know about all this? We have, for the last 2 years, made a screening of the manufacturing companies in Denmark and how they work with additive manufacturing. And it has actually been quite interesting. I hope I turn this right. This is also available in reports, but we actually see that we have the domains down here, are the rapid prototyping, innovation, tooling, and direct production. But then we also have a maturity X, where we see that either you have almost, actually you don't use it, or you buy it from service providers, or you have your own printer, or at the top level, as we defined it, you both have a printer, but you also collaborate with others. What we see is that 75 to 76% actually don't use additive manufacturing. And from the rest, 80% of those are actually using additive manufacturing as R&D related activities. Maybe they'll also have in other domains, but that's the primary domain. What we see is that it spreads actually towards direct tooling. And this is the reason why we took you into our manufacturing area to give some examples. Just a short example of what it can be used for. It is extremely fast to design models. This is our master students getting a task to try and make different, and you can see bright colors, but you can see different designs. And especially you have different faults and so on, but it's a very steep learning curve working with this. The task was to hold a box from our inventory, and it should be able to hang on, and it actually works. The good thing is it also that we have them in different versions, and if they break, we can actually just print a new one. If we really need to make sure that it holds, then we just design a new design, and then it's much more stable. Again, alternatively, we can also go on to our service providers to have them made in metal or in other materials, or have them made even more in conventional processes. I think it's interesting also to see that we can combine different tools, because they were actually asked to make quick changes between different grippers, and now we call them a gripper here. And we had to use a hook also. So instead of having to change, they actually just developed a modular system where we can stack them. And this is also one of the benefits when you have this direct tooling, that you can have all your goes and tries, and then you can combine it. And if you want to use another one with a different set of, then you will just print a different one. And many of these things, as soon as we talk about, we have them in our digital backbone, so we can just retrieve our drawings and everything from there. Moving to a little bit more advanced here, we talk a little bit more in modules and platforms. Instead of having to change our grippers all the time, we have a standard gripper, and then our robotic guys, they have designed the gripper tips, and they have been both printing the fixtures, the grippers, and they need to be put in the right way. Otherwise, of course, this is not able to grip it right. But again, we can do it over and over again in different iterations until we have the right configuration as we want to. Also, designing a platform, and this platform is, we have magnetics in this, so it actually goes to our transport conveyor band. And here you can see we are trying to assemble a drone engine. So we have the little motor engine, we have the propellers, we have the screws, and here we have the container for the final one. And all this is done on a relatively simple FDM printer. And if we have to go big scale on this, of course, we can just print it on another technology or have it made more conventionally. So this is just some examples of how we do it. We also have examples of molds for vibration feeders, and especially within the mold area for injection molding, I really see some potential in having a very flexible setup in making inserts for the molds and so on to adapt to customer variations, but also for lower quantities. So these were some of the examples and also to turn back to our screening from the manufacturing industry, we saw that those companies who work in multiple domains, but also have both your own printer and work with service providers, they have a radical higher level of innovation, both in process and in process and product, than those who don't work with additive manufacturing. There's also an argument of developing your organization as an innovative one. I know time is running, so just to wrap it up, it's something about getting started and getting curious, and you're welcome to address us. So are there any questions?
Yes, we have a question from Edvard. Please go ahead, Edvard.
Yes.
Yes, hello, my name is Edvard Lorentzen from Teknik Arbejdsgiverne. I will ask, will additive manufacturing change the way that we produce things?
We hear a lot in the media and also from some sources that this will simply be the new thing that will change everything. I don't think so. I think it will be a supplement, and it will help us be able to be much more flexible in our manufacturing. There will be some products that are, as Said also talked about, that will be very good for this one, and it has to be redesigned, but it will not, everything should not be printed. But the right things should be printed, and then we should go hard on that. I more see this as a technology adoption that will help companies become much more innovative, both in development of new products, developing the manufacturing setup, and then finally also the product. So it will change something, but not all. I hope that was answer enough.
Thank you.
So we have another question from Johnny. Please go ahead, Johnny.
Hello, my name is Johnny Jarhal from Robotic in Sweden. My question is, which strategy should be followed when working with additive manufacturing?
What's actually interesting here is that because it's a multi-purpose technology, I also see that we should follow multiple strategies depending on where we are in our manufacturing and in our maturity level. So if you don't have any experience in additive manufacturing, I really see you should buy a printer. You should get curious. You should engage the organization. You need to have your managerial level involved, and then you should start trying to print different things. And then you should engage in the network. The AM Hub, I also think they participate in this dialogue today. They have mapped the entire ecosystem around additive manufacturing in Denmark, both suppliers, knowledge holders, and so on. So engage in the network, get some experience. And if you have already engaged in your additive manufacturing journey, then you should be much more strategic about it. We have developed some frameworks around it. And feel free to contact us for further. Yeah. And then actually there's one question more I hear.
Yes, there's one more question from Sigurd. Please go ahead, Sigurd.
Yes, hello. Can you hear me?
Yes.
Yes. My name is Sigurd Rosendahl, and I'm from GEA Process Engineering in Søborg. Yeah. You were showing some graph on the paper. Yeah. Showing additive manufacturing in companies. Could you tell me which report you got this paper from?
Yes, we have published 2 reports for the 2 last years in collaboration with Additive Manufacturing Hub. I can, if I get your email afterwards, I can send you directly for it. Otherwise, on the AM Hub website, you can get a short version and a long version. So the much more elaborated data is selected data I put in here. So yeah. Was that okay?
There are no more questions, at least. So
okay.
Hi.
Yes, thank you
Christian.
very much.
I'm professor at SD Robotics, and I want to invite you to Curious Today Partner Tomorrow. The next instance is going to happen on the 27th of October. What I'm going to talk about on the 27th is additive manufacturing, but a large scale. So one of my partners, Copot, they are one of the first companies worldwide who actually take additive manufacturing and printing of 3D concrete houses to the next level, an industrial level. And here in the lab, we have some students working with their materials, so this is some test prints, but this is, of course, obviously not large scale. So if you join us, you will see how we take this to full buildings, even towers. Be around, and we will have a walk over one of their construction sites.
Okay. So hi, I'm Christian Schlette. I'm a professor at SD Robotics. And I was invited to talk a bit about additive manufacturing with concrete. So it was a Danish company, 3D print house, who started out with printing plastics, but then they took the very same technology and just scaled it up in order to be able to print concrete just like with a giant 3D printer. And this is an example of what they print. You see some structure here from the different layers as they print the concrete right now. And this is something that we use together with our students in the lab in order to work with the materials, to have some experiments, how they can, for example, be reinforced using some wall binders. This is something that we do with our students because for the company, it's quite interesting to have our master students being on their projects. We are directly working together with them in the IFD-funded project NextCon. And NextCon includes this partner, Cobot International, as well as Bjarke Ingels Group, DTI, CIH, concrete company here in Denmark, and many others. And we are working together in order to cover all of the process steps to actually have a house designed or building or infrastructure designed, and then also to print it in 3D concrete. So the process involves the architects to start with coming up with the designs that they want to print and handle. For example, of a building, we are currently discussing to also have a demo where we build a row house in Denmark based on the same technologies. So it's about the architects coming in, building it digitally, and then to process the data into G-code that is then sent to the machine. And it's a bit handled differently with the two partners. So Cobot International, they have a giant gantry. A gantry being like a 3D printer, just scaled up to dimensions of, for example, 12 by 12 meters. And then to have an extruder that is walking along as in a 3D printer, but producing layers of concrete in order to have the structures here curing out over time, building a house step by step, layer by layer. The other approach is with our partner CIH in this project. They are producing or using the same technologies just off-site. So they have production facilities where they have robot manipulators running on linear axis in order to produce some of the structures that are then carried to the construction site and then put into place on the construction site, where, of course, the Cobot approach is on-site in comparison. You have the structure and you print as you go. So then we have already the other partners in there who look into material properties, really to go into the properties. So this is not even concrete, it's a mortar. So there are many different material properties that are still under research. And we are working together with international experts, for example, from ETH Zurich, in order to get the material properties right, to have a stable building as you would get from normally poured concrete. What are we doing with this at SDU Robotics? We are supporting the partners regarding the data that comes up, because 3D printer can just be seen as a huge robotic system. And we are building digital twins. This means we are helping Cobot and the other partners to have a digital twin where you get in the data. We can already process it. We can simulate.
Sorry, Christian, we just lost your sound. Could you please just have a look if you need to unmute, maybe?
Okay, can you hear me again? Yes. So
yes,
let's start with the digital twin again. The digital data comes in. We use means of simulation in order to have a simulated gantry from Cobot or simulated manipulators who show the process and who help us to already analyze the process in advance. So we can tell how long it will take to print a building. We can already simulate the properties of the building, such as, for example, how many square meters we have on the surface that then can be processed by different means, for example, additional manipulators on the construction site. Coming back to our students here in the lab with the master students, they are now looking into the properties based on those digital twins. But as you can see, also based on the different setups that we have here, then we have experiments where the company looks into the different options projects. This is it from my side, how actually 3D printing is brought to the large scale. And I would like to have some questions from you if there are any.
Yes, thank you. We have a question from Sten. Sten, please go ahead.
Yes, hello, Christian, and thank you for some nice inputs. What system is Cobot as a basis for printing large structures and robot manipulators?
So as I said, it's a gantry system. So it's really like a big square that they are spanning over all of the construction site. In comparison to the solutions that are also around in 3D printing, that's the manipulator, where you would have to position the manipulator over and over again in order to get the full print. But with the gantry, you already have a structure that is overspanning, overarching all of the construction site.
Yes, thank you.
Are there further questions?
Yes, we do have a question in the chat as well from Jesper. Jesper, please go ahead.
Yes. Can the robotics research contribute to a project in the construction industry?
Well, there are already many technologies available regarding 3D printing. And if my colleagues are going to talk about 3D printing, then it's the basic controllers that are sometimes even open source technologies that are available in order to have a printer. Cobot, for example, took those technologies and scaled them up. But what we can contribute is to have, for example, collision-free movements with the robots, with the extruder in an ongoing print. So not to run into any fresh prints accidentally. If, for example, the extruder needs to be taken back to a maintenance area, for example, to be cleaned or to be maintained. Are there further questions?
Yes, we have one more question in the chat from Christian Dam. Christian, please go ahead. Christian, you may need to unmute.
Yeah, hi, I'm Christian Dam from the company Robot at Work, and I'm just looking at these very nice samples, and yeah, just wondering what is the nozzle size that you use to print these, and also they have a very nice surface finish. I'm just wondering if they have been post-processed in any way.
So this side here is a clean cut. This is a bit artificial, right? The quality that you get directly from the prints you can see here, and this is not finished or without any surface treatment. What they have is another size of, it varies, but it's about 7.5 centimeters that they have. And then they also have active flaps that are regulating the overshooting concrete. So this is why they actually come to the outcome that is already quite straight, and with a bit of grinding actually already makes a finished surface.
Okay, thank you. I think maybe we have time for one last question. I'm not sure how much it's a question, but Thijs, please go ahead. Are you there, Thijs?
I'm not the only one asking this question. Yes, can you hear me?
Yeah, I can hear you.
Hello?
Yeah, go ahead.
Okay, my name is Thijs Lindstrøm. I'm a business developer from SDU. Yeah. And I really wonder why you don't show something real, how it works. Several people asking this question.
That's a good point. Actually, we had an appointment today at the construction site, at a site where they are printing right now at Køge. But due to Corona, we had to move everything online, and this is why I'm stuck in the lab. I would also love to be with the guys and to see actually the current print they are working on. It's huge. You will see about it in the media in a bit. But unfortunately for today, I have to stay in the lab and just show those pieces of material that they produced earlier. Sorry for that. I hope we can have another excursion where we can really be at the construction site and show what's going on.
Hi, I'm Roberto Naboni, and I'm assistant professor at the University of Southern Denmark at the section of Civil and Architecture Engineering. Here at the Create Lab, we are studying how to apply additive manufacturing in the field of construction and architecture, ranging from concrete 3D printing to plastic 3D printing, composites, and others. If you'd like to know more about our research, come on 27 October, Curious Today, Partner Tomorrow. See you.
Okay, fantastic. So, hello everybody. So my name is Roberto Naboni. I'm assistant professor at SDU Civil and Architecture Engineering, where I'm studying a field that is called computational design and digital fabrication. Today I'm going to talk to you about our work in computational design for additive manufacturing, and specifically we're going to speak about what we do for design and construction application, also following up on what Christian just explained in his case. So I would like to start with a broad question if you want, but this question is about why additive manufacturing construction. So of course, additive manufacturing is bringing a lot of advantages, but I would like to a little bit take it the satellite view and then zoom in some projects. So we have a couple of reasons. One of the main reasons that we're looking at a huge amount of material that we use every year for construction purposes. This is 42.4 billion tons, which is a huge number, and we can tell a lot about this, but one of the main goals that we want to achieve with additive manufacturing is actually minimization. One of the goals that we're looking at is the second one, is basically the reduction. Second goal is minimization of the carbon emissions. So construction is responsible for directly and indirect 40% of the CO2 emissions worldwide. And of course, additive manufacturing can help in minimizing this. But while minimizing the use of resources and carbon emissions, we also have to provide about housing and buildings for 2.7 billion more people in the next 3 decades. So this means that we have to build more, we have to build with less resources and more efficiently. So this is somehow the challenges that we have in front of ourselves, and we believe that additive manufacturing can help in doing this. So I'm going to show you 3 projects, starting from biopolymer extrusion to concrete 3D printing, and there will be a range of approaches that will try somehow at addressing these problems. So the first project is called Trabecular Pavilion. Trabecular Pavilion is essentially using biopolymers and printing and additive manufacturing aimed at material optimization. However, this is a kind of setup that we use for fabrication, which is essentially a kind of 3D printing, fused deposition modeling. And we started thinking how we could build a more efficient and more structure of bones. So we got inspiration from the internal microstructure of bone, which is a porous structure, is a cellular structure. It's very lightweight and very optimized for high loads. And we look into this to essentially get inspiration for our work. And we started also with material testing for 3D printing and biopolymers. Referring to this image, you can see on the left side, essentially an elastic kind of a lattice brick, which works in compression quite well. But on the right side, you will see a rigid one, which has a different topology and can withstand up to 1 ton in compression, which is 4,500 times its own weight. So that's very much for a small sample of plastic, 220 grams. And this is giving you information about how you don't really need to have the most impressive material, but you actually need to use material and geometry in a smart way. So this is various experiments about different topological variation of this kind of lattice work. Anyways, topological variation, workflow. We spoke about computational design. So you can see here this kind of scheme where you can see in the top part what we call material and fabrication system, where we take into account a fabrication setup, printing material, essentially the material characteristics, and we transform this into cellular structure, where because of additive manufacturing, we can take into account in the computational workflow already, the tessellation already, which means the size of the elements we're going to work with, the geometry optimization and interlayer design. And on the bottom side, you can see this that we call computational system. Basically, we define an architectural shape, in this case is a shell structure, and then we apply loads and we use a finite element engine in order to compute where more material is needed and what kind of layout this should have. So this is an image of the progressive material organization that you would have over a shell. So the white areas are where you need more material, and the black areas where you need less material. And following this, we have several layers of optimization. It's an algorithmic process, so you don't really design like you would do normally for a building or such a structure. You actually use algorithms that help you to automate the design process. So this is an image of the results of this investigation. You can read this lattice work. It's very lightweight. It's almost porous and have this different organizational material. You can read the topology that is behind this, but also you can see that we print at very high resolution, 0.5 millimeter of layer resolution. And this is also controlled because you have a possibility on the base of the angles that you print with to organize the material and also to make it more material efficient, and also to be able to guarantee an isotropy of the mechanical behavior. It's a wide topic, but I'll let you with this for the moment. So these are more images of this project. And what I want you to read is probably here the bottom line, where you can realize that this lattice structure is actually a variation of a weight to area ratio of between 6 to 11 kilograms per square meters, which is essentially comparing with 10 times less than a similar construction system that can withstand mechanical classes of similar type. So we started thinking how to extend this plastic-based printing towards construction that is mostly made in concrete. And we look into using additive formwork. Additive means, again, 3D printing made of plastic for formwork construction. And the reason for doing this is that essentially we have larger 3D printers in the lab that we can afford to 3D print formwork that can be used for concrete elements. But why to use 3D printing for this is because we can use not of voluminous formwork elements, we can use thin shield elements, we can have high geometric freedom, and also since it's plastic, we can reuse it a number of times, or we can recycle at the end of the life cycle. So what we did is combining what you see in the left, which is basically thermopolymers, which what you see on the right, which is ultra high performance concrete and metallic fibers, which allow you to gain additional properties in tension. And I'm going to show you basically the workflow that we utilize, where we have always at the first step, the computational design, where we do the design parametrically, we have analysis, and then we have G-code generation. We transfer directly data to 3D printing robots in order to have a seamless connection between design and fabrication. But also we have formwork 3D printing, where we always gain this feedback with 3D scanning and compare the precision between the design model and as-built model. So we have tried different type of materials. We also look into material recycle of different type, PTG, ABS, PLA, and polypropylene. And what you can see here is that we studied with thermal camera imaging what kind of is the behavior of the thermal process of 3D printing and how this would influence distortions. And here you can see a fast comparison where different materials can respond better to the 3D printing process and allow higher precision. So at the end of this process, what you can obtain is 3D printed formwork of this type. This is up to 1 meter in height. And then you can pour in concrete. You need a kind of self-leveling concrete, which has good properties of getting into narrow geometries as well. And this is basically a comparison between the 3D printed model and actually the model that you obtain afterwards with concrete. So this is also to show you that you can obtain such geometries that with other formworking technique wouldn't be able to achieve. You can have a topologically complex kind of structures of this type. And this is because you have digital tooling that can allow you to integrate basically 3D printing analysis and also an optimized, let's say, generation of the toolpath for 3D printing. So this is kind of a big, large-scale sample of the kind of intricacy that you can achieve. And these are more images. We also have extended this process to smaller panels, 50 by 50 centimeters. And here you can see a section elements where the formwork is very thin, and you can obtain such panels with the geometries varying from around 1.5 centimeter to more. We got 3D scanning to understand deviations are within control. And now, since they're signing me that I have 1 more minute, I will give you a little slideshow and I get to the very last topic. Okay. Yes, and this is about robotic concrete reprinting. Christian has mentioned to you before some of the research that you were doing on this topic. This is in parallel. It's about using robotic arms for concrete 3D printing. It's something that we started this year. And this is essentially how you can use as a 3D printer a robotic arm and you can build up such geometries and such elements in a fast way, and also aiming at minimizing the material usage. So in order to do this, we use, let's say, a kind of a cell that has a concrete pump which is connected to a robot. Robot is moving in time, and it's a quite fast kind of approach to building concrete elements with 3D printing. You see here a layer height of 12 millimeters. So in comparison with before, we have a relatively high resolution. But also what you can get here is working with geometries such as this plain circular column, which almost has a smooth finish. You can still read the layers, but this is a kind of a regular geometry, but also you can then vary thickness of the elements, just working with the speed of the robot, or working with the more intricate toolpath generation, as you can see on the right side, and get these decorative elements, which also allow you to gain other mechanical performance. So I would say this is all. I just get to the end of the presentation. And these are my contacts and our website, and I'm open for questions if you have any.
Thank you, Roberto. I think we will take any questions in the chat as we have run out of time for this. And then we will continue to Alireza for the next presentation.
Okay, thank you.
Yes, my name is Alireza. Today I want to give you a brief information about my talk on the October 27th. As you know, my research focus on smart material, additive manufacturing, and adaptive structures. So what we're going to do on the 4D printing, we're going to use the smart material to print some metamaterial or adaptive structure, which are able to actually transform to the fourth or extra dimension by changing temperature, moisture, electric or magnetic field. So it's what we're going to do is kind of magic. See you on the October 27th.
Welcome to Careers Today, Partner Tomorrow. My name is Alireza from Mechanical Engineering STU. Today I'm going to talk about the 3D, 4D printing of adaptive structures. Before I head into this subject, I would like to introduce you with some smart material. The typical one, maybe every of us introduced with that, is a piezoelectric material. Piezoelectric material is a group of smart material that are able to sense the deformation and transform to the actually electrical energy. At the meantime, they have the reverse effects. They can be actuated by the electric field and produce some deformation. The other group of smart material, we can mention about the shape memory material. Shape memory material, they can actually show some shape memory effect. Shape memory effect, as I shown that here, is a cycle of thermomechanical loading that during this cycle, material actually experience to gain and at the meantime recover large amount of strength. Regardless of the dimension of the printing, somehow if we using the smart material for additive manufacturing, what we fabricate has actually a magic configuration inside that can be actuated by temperature, moisture, electric, or magnetic field. This phenomenon is so-called 4D printing. Let's focus to the shape memory polymers. As you can see, the key feature of the shape memory effect in shape memory polymers is transmission between the glassy to rubbery phase. Shape memory polymer, they are stable at the low temperature in the glassy phase, while at the high temperature, they are stable in the rubbery phase. Glassy phase, as you can see, can produce some elastic plastic property. At the meantime, at the high temperature, this material has a property of pure hyperelastic. Here we have a cycle of thermomechanical loading. The first feature of shape memory effect, as you can see here, can be actually a product in the high temperature. In this way that at the room temperature, we heated the material. After that, material experienced the loading condition. At the fixed strain, we can unloading. As you can see, if you follow up the diagram, during this cycle, actually material move to the temporary configuration, while this configuration is not permanent, so by the heating and cooling process, it can be recovered. If we add this feature in the additive manufacturing, as you can see, at the first stage, we can fabricate the material or structure using of the 3D printing. The programming can be done in the other stage. As you can see, we can rise up the temperature, add some loading and change the shape. At the fixed configuration, we can unloading. What we gain is a temporary configuration. This temporary configuration can be actuated by the heating and cooling process. Let's see what's happening. Here, we designed some multi-layer beam. This beam is fabricated by the two different shape memory polymers with different glassy temperature. As you can see, by increasing temperature, this smart hinge can be closed and open. So based on the additive manufacturing, as you can see, a smart material can produce some motion, can add some extra configuration to the structures. It's just a phenomena that we just experienced that in the lab. By inspiring of this actually phenomena, we can fabricate some small lattice structures. Here, based on this phenomena, we designed some unit cell that actually consists of the 3 different shape memory polymer with 3 different glassy temperature. By optimizing this unit cell, somehow we can provide some motion of opening and closing of lattice structure. As you can see, this lattice, by increasing temperature, is open. By increasing more at the higher temperature, this lattice it will be closed. It's the sequence of activation of each layer can produce this opening and closing motion. The other effect of shape memory material in additive manufacturing is the programming inside of the 3D printer. It means that during printing, the programming happening at once. It means that the 3D printer melted the shape memory polymer, and by moving some deformation, some strain induced inside of the 3D printer, this configuration can be recovered by heating and cooling process. The key point of this phenomena is that every structure which made by FDM process or other additive manufacturing technology, they are made by a sequence of the layer. Based on the moving speed and also the gradient temperature inside of the material, some strain induced inside of the structure. This strain by heating and cooling can be recovered. Here we have, in the right-hand side picture, we have a ribbon is made by shape memory polymer. After printing, this material subjected to heating and cooling process. Depend on the printing velocity. As you can see, we have different curvature after heating and cooling. Based on this phenomena, we can use this kind of feature to design some 3-dimensional configuration. In this way, that by just printing the plain structures, we can generate 3-dimensional geometry. This kind of feature can save time, at the meantime, a lot of material as well. Here, we designed 2 different simple geometry, circular and the square geometry. The key point of this deformation is the pattern of printing. The pattern of printing in the circular is the helical. The pattern of printing in the square is a rectangular one. The result, as you can see, is remarkable. We get the conical geometry, and at the meantime, we get some 3-dimensional configuration. The other feature of shape memory effect in shape memory polymers is the cold programming. It means that the material at the room temperature experience the loading and unloading, and we achieve to the new configuration. This configuration can be actually recovered by heating and cooling process. It means that we can print the structures. After that, we can change the shape on the desired geometry. This desired geometry can be recovered by heating and cooling process. As you can see, this cycle is shown as a stapler in the right-hand side picture. By taking advantage of this cold programming, somehow we can use this shape memory polymer as a solution for bumpers in any moving vehicle. Here, if we fabricate shape memory, if we make some bumper structure by a shape memory polymer, if this bumper is facing but minor damage, this damage can be recovered by just simple heating by hair dryer. At the right-hand side picture, as you can see, shape memory polymer can provide a huge damping capacity as well. Here I mentioned about some references that you can follow up and get more information about the 3D printing of smart materials, or either you can keep in touch with me via email or the website of STU. Thank you for your attention. If there is any question, I would like to answer.
Yes, thank you. We do have one question from Peter. Please go ahead, Peter. Peter, you need to unmute.
Thank you. You talk about polymers, which may not have enough strength in practical and industrial applications. What do you think about that?
Actually, you are right, because I can approach to this question in different way. First, in some industrial application, we may not need more and huge strength. As I mentioned about car bumper, we can look at this in a different way. At the meantime, what I talk is about the shape memory polymer. We have the shape memory alloys, they made by the nickel and titanium. But the point is here, the printing process of the shape memory alloy is much complicated and maybe is costly. So shape memory polymer is a good choice to practice, to actually try and error and get insight to implement into shape memory alloys structures.
Okay, thank you. I believe there are no more questions.
Thank you.
So we will move on to Andre. To Sønderborg.
Hi everyone, welcome here to STU Sønderborg, where we are in our development lab, the core. I am Andre and I'm going to be part of the second event of Curious Today, Partner Tomorrow. And I would like to show you, among other things, an application for resin printing, where we have a topology optimized knee pad with embedded deformation sensing. We are going to show you a lot more cool stuff, so just join our meeting and see you all there. Better. So hello everybody, my name is Andre. I'm an engineer here at STU Sønderborg, and I'm going to talk a little bit about advanced applications for additive manufacturing, including how we integrate 3D printing into mechatronics in our section. So I've been doing a PhD for the last 3 years on this, and why did we choose additive manufacturing? Well, it's no longer a novelty and hasn't been even back 3 years ago. But we wanted to exploit these virtually limitless geometry options, and also to look into the broad range of exotic filaments which were available for FDM printing. They have special properties, these filaments, among which the conductive properties were something we wanted to integrate by means of printing a conductive part, a non-conductive part in the same print, and then including a standard component such as a DC motor. Basically, we're going to sandwich this. So we only have a full mechatronic product with only a standard component, conductive and non-conductive printing, without using wires or other classical joining methods, and that's important. Now, there are, of course, drawbacks to this. The conductive filaments, they will be characterized by lowering their resistance by increasing the pressure. So basically, you really have to squeeze hard on these conductive filaments in order to achieve the necessary level of conductivity. Indeed, we made some snap fits to put a motor inside. We calculated some dimensions. I'm not going to bore you with the math in that. But basically, what we achieved was that by turning on the power on the setup without use of wires, we managed to turn the motor on. And you can see I'm very fond of this video. It's the first video I ever made in my PhD. So this was the first case study we made. However, it's very rare you're going to carry a power supply with you. So instead, we went further to an optimized autonomous design where we include an onboard battery. So we go away from the power supply, we can carry the power ourselves. Because of the directional forces we have to ensure by inserting the motor, this lends itself very well towards topology optimization. And we have done this in the first study. So we have removed material, almost 50% of the material removed, while achieving the same power output. And you should be able to see it if I would stop being trigger happy. But yes, so you have a fully autonomous mechatronic product right there by means of very cheap FDM printing. Furthermore, we have a control interface. I don't know why this vanished, but what we're doing here is we interface between an Arduino microcontroller and a temperature sensor by means of 3D printing, because while the conductivity of these filaments is not very good, it still lends itself very well towards digital signal levels. So we can really integrate smart devices, even the microcontroller on board with a sensor. This approach so far has been about getting rid of wires and only using 3D prints along with standard components. Now, as a collaboration between SDU and Youngstown State University in Ohio in the States and Youngstown Business Incubator, where I've done my PhD exchange, we have investigated how to actually go the other way. So to fully integrate metal wires and components directly into 3D printed substrates. So this is done by overmolding, or you would know it by polymer welding. You basically take two 3D printed parts and you sandwich them together by having the wire or the connector inside. These are some samples. You would use typically vat photopolymerization, so either SLA printing or DLP printing. DLS was the technology we use here. It's just a fancy name that the company had at that time. We have the case study. We love making these case studies. One was to 3D print a jack, which we overmolded. And the whole idea was that we would sandwich the wires between the two parts before they were being cured. And then we could insert the jack and then use it for some power applications. And you can see that the conductivity, guess what, is that of the copper wire, which is inside. So we were very much below 1 ohm. That was one case study we did with this. The next thing was we looked also at these lattices, which are so popular nowadays. We started by getting inspired by some wearables, which were the Adidas Futurecraft shoes. You can see the sole of these first 3D printed shoes a few years ago. We did some topology optimization by removing material, as you can see on the top side of the screen. So we have roughly the same behavior for only a fraction of the material again. And of course, we want to integrate sensors. So what we did is, you can see the lattice on the lower side includes a pressure sensor, which when actuated actually records pressure. So you can see that the harder you press, the bigger response you get. And that's, again, a simply sandwiching of electronics in between these uncured layers. The last thing, and this is what we're working on currently actually, is to work with wearables. We're going to have a knee pad. So for somebody who wants to sit or has to sit during their work time a lot on their knees, for example, a tiler or somebody who lies tilers on the ground. Again, we employ topology optimization because we have a 3D printed knee scan. So what we make is a dedicated custom shape for the specific person and for each knee the specific person has. We're using topology optimization, which again is super good at handling these differentiated loads. And the outcome is that we have used flexible tactile sensors embedded between these layers. They are printed in flexible resin because there have been advances in the materials for the resins as well. And we have a knee pad which is capable of deformation sensing. In order to test the quality of it being able to record data, for example, you can tell the tiler, oh, sit straight, or you want to be able to record how often he is losing his position and so on. We wanted to test this, so we attached it to a robot arm. And you're going to see that depending on the angle and depending on the load that is being applied, you're going to get different taxels, so parts of this tactile sensor being activated. So indeed, we can tell between, is the guy sitting on his left or on his right, or is he leaning backwards or forwards? And this again was done by taking some flexible tactile sensors, putting them between two parts, which can be 3D printed by simple SLA prints. We use the Formlabs, which is an accessible system here at Sunnable. We use the same system for all of the case studies, also the ones we made in the States. But again, this is not exactly FDM, but you're not going very far away in cost from FDM. As a small bonus, we're also looking into conformal printing, because you have seen that the knee pad was constituted by a scan of a knee. But what if we had a surface which we could not scan? What if we actually wanted to print directly on a surface which is not flat? In that case, we took the audio jack again, and we have a simulation done by some master students in an MDB project where we are actually printing conductive filament onto an audio jack. And the whole idea is that when you remove it, this audio jack is going to be able to be interfaced for each channel in the same way that we have managed to achieve through SLA overmolding. So this would be an FDM process, which achieves the same result comparatively with SLA by use of conformal 3D printing. Yeah, so these are just a few ideas of what we are doing here by integrating additive manufacturing into mechatronics. I'm very open to any suggestions and any collaborations because we have a lot of desire to print and we have a lot of desires to obtain objects which actually function. So at this point, if there are any questions, I would be very happy to address them.
Thank you, Andre. We have 2 questions, and we will start with Niels. Niels, please go ahead.
Yes, hello. Niels Corsair from Gain & Company. We are independent advisors within automation and production. I just got a short question. Can we actually expect filaments with better conductivity in the future?
Yes, thank you for your question. I'm just going to say it out for the people in the room. So we have a question on, can we expect better quality of conductive filaments in the future? And funny enough, this morning I have received a new brand of conductive filament, which displays characteristics of up to 20% lower resistance than the ones we have used in these studies. So while I have mentioned we have restricted ourselves to low current applications, this doesn't seem to be an issue anymore. It's a lot more expensive than the previous ones. We're talking 5 times more expensive than classic filaments, but it achieves actually conductivities comparable to classical PCBs. So we can enter a whole new market with this. We're talking about 10 to 15 ohm resistance, which is no longer the 400 ohm we face so far. So yes, we can expect that these filaments are also going to improve and we can achieve better applications thereby.
Thank you. We have another question from Søren. Søren, please go ahead.
Yeah, thanks. Hey, Andre. Thank you very much. It was really, really interesting. My name is Søren from Danish EM Hub. I have a question regarding the cost. What is the cost between the resin printing and the classic FDM printing you were talking about?
Yeah, hi, Søren. Thank you for your question. So the cost difference between FDM and SLA, of course, is dependent on geometries. It's depending on how much infill you would use in FDM and so on. But roughly, SLA is the more expensive product. However, if you look at surface finish, SLA will definitely compensate for the fact that it's more expensive. The fact that you can overmold it and include electronics after you have finished the post-processing also means that you alleviate the risk of, as in the case with FDM, electronic insertion, where you can put the electronics inside the FDM process while it's still running. Henceforth, if the process fails, you will lose the electronics. Here, with SLA, you can insert electronic components after the curing or after the print has been done, so you don't expose yourself to these failures. So yes, it is a bit more expensive to do SLA, and the printers might cost a bit more. You can get Formlabs for 25,000 krona perhaps, where you wouldn't get there with FDM, cheap FDM printers at least. But I would say that the price, depending on your application, really, really pays off if you know what to choose.
Thank you, Andre. That concludes the questions, I believe, meaning that we will go back to Odense and Morten.
Yeah, thank you.
Hello, everybody. Can you hear me? I can even turn my own camera on. Yes, I just have 5 minutes. And you heard the bell, and that is Nana trying to tell me that the 5 minutes are already up. So I'll do it real quick. We have seen a lot of our researchers today that have talked about what we actually do at STU. Just before we move on to our very, very, very interesting partner, Additive, that I'm really looking forward to, I'm just going to say real briefly, how can you, as a participant in this event, and at any time get in contact with us, and what can we actually do for you? We can do research on a consultancy basis, hourly basis. We can help with all sorts of research and development, and also in terms of education, semester projects, bachelor thesis, internships, guest lectures, site visits, student jobs, and we can also start actual research and development projects with you. This, of course, is interesting both for the industry, but also for the researchers sitting internationally. You have seen some of the things we can do in additive manufacturing. As you know, we are very strong robotics. And once we get to the next event in Security Today, partner tomorrow on simulation, you will also see what is our strongholds there. And we have capabilities to both write applications with companies and with other partners of the university and GTS partners or RTO partners nationally, internationally. So this would also be a very good time to get in contact with us. And who are we in this situation? Actually, you should get in contact with the head of tech innovation and have his contact details here. It makes really no sense to just stand here and read his contact details. I will make sure when I send an email that it is sent to everybody. And you can see that the process, you contact us at the Dialect project scope agreement, and then there's a project execution, and this can be anything from weeks to years. All right, just moving on. Don't forget the DACAS, Rob, the Academic Society of Robotics. And they have the second webinar of 4, and that is on the 4th of November, and that is focused on Aalborg University. If you want to join us, please do that on the 4th of November. And also, if you want to see the first webinar, it is online, and you can find it on the DACAS Rob website. On the 5th of November, we have, this is Danish, but I'm pretty sure most of you can read it, Innovative Robots in the Health Sector. And if you cannot get enough of knowledge on the 5th of November, you can also join our very esteemed colleagues. You just saw some of the things that Andre did. They just blows me away how incredibly good they are in Sønderborg. You can join the industry day there on the 5th of November, and these are all online events, obviously, because we're in a situation where it's really hard to meet. Yes, and just again, I said this in my introduction, but I'm just going to say it again. Curious Today Partner Tomorrow will take place every 6 months, and the next is on the 21st of April, not 2020, but 2021, of course. And the next topic is simulation. And with those words, I will give the talisman on to our very interesting and very focused and very enthusiastic partners in Jyllinge, namely Additive. And Lasse, I've really been looking forward to this presentation from you. So. Take it away.
Hello everybody, my name is Lasse Ståhl and I'm the CEO of the 3D printing pioneer Additive. We build machines like the one here behind me to enable the manufacturing of high precision injection molded tools, and these we use to compress lead times while at the same time saving costs and risks. What we do, I guess, may best be explained with a little example. What we see here is a 3D printed injection mold insert. It has 3 parts that we may put together to form a cavity. The cavity we then insert in a mold tool like this one to stabilize it, and then follows the injection molding itself. Injection molding may be done using an injection mold machine like this beautiful Kraus Maffei. We may also use a baby blast like this one, or alternatively we may use a Dr. Boy, which was kindly provided by the Southern Danish University. Thanks a lot for that, guys. And after injection, we may be left with a component like this one, which is done in a medical grade TPE material, which is sterilizable and very nice for medical devices. We may also, as something quite unique for freeform injection molding, wind up with a component like this one. If you want to know how we manufacture stuff with an injection molder that looks like this, I suggest that you spend a little time on October 27 to participate in the event Curious Today, Partner Tomorrow.
Thanks a lot for letting me on stage. Can you hear me now? Great, good starting point. My name is Lasse Ståhl, I'm the CEO of company Additive, 3D printing pioneer. And we believe, as I mentioned on this first slide, to have the most versatile 3D printing platform on the planet. Additive was founded about 5 years ago with the modest ambition to automate additive manufacturing. We've moved a little bit further on since then. We have about 30 employees, most of them sitting here in Jyllinge, but we also have a sales guy in the US who's taking care of the American market. We've been selling our machines in the US, in Germany, Japan, Belgium, quite a lot of places, as a matter of fact. And we most recently established a collaboration with Mitsubishi Chemicals to make sure that a lot of other people can also benefit from freeform injection molding. The stuff we have been trying to solve lately at Additive has been the transition from the product development phase into the production of components. Everybody knows, at least everybody in this audience knows, how nice 3D printing is for prototyping. You have the opportunity to run wild on designs, you get short lead times and you get low costs. But the problem is migrating away from the sandbox and into the actual production. That's where you have to start concerning yourself with tolerances,
with production grade materials and scalability. And at Additive, we've asked ourselves the question, what would we get if we tried to combine the benefits from 3D printing with the benefits from injection molding to arrive at a more flexible and more scalable production platform? The answer we came up with is what we call freeform injection molding. And that is a technology that has three unique aspects of application. The first unique aspect of application is the product development. We share that application with everybody else. But the big difference is that it's infinitely easier to migrate out of the sandbox with freeform injection molding than with other 3D printing technologies, because you're basically injection molding from day one. I'm going to show you that a little later in the day. So we do a lot of stuff in product development. And then once you have launched your high runner and have started producing lots of components with conventional injection molding, you have the unique benefit of being able to customize those products because you already defined in the product development stage a recipe for low volume manufacturing. That same recipe can also allow you to make spare parts on demands if you don't want to produce them to stock. And by creating this platform, freeform injection molding, we are efficiently turning injection molding into the perfect life cycle management tool, because you can start producing from day one with injection molding, and you can scale all the way into the millions and billions of pieces, while retaining all the time the ability to move back to low volume manufacturing. You reduce your risks of launch, you reduce your waste in the development process, because you don't have to concern yourself with minimum order quantity. The smallest quantity you can produce with freeform injection molding is a batch of one. I'm also going to show you that a little later. The process itself is deceptively simple, and since I'm going to be walking you through the floor here at Additive in a little while, I'm going to skip this. Suffice it to say that we print injection mold inserts. We fill these inserts using conventional injection molding machinery and materials. And then we can either take molds apart like you would any other injection mold tool, or we can dissolve them. The dissolvability is really the big kicker here, because that allows you to take the design freedom for 3D printing and move it into the injection molding space. At Additive, we concern ourselves mostly with the sale of machines and materials. That's our main business, and that's what you should expect from us. We, of course, want to support you with evaluating the technology, but we are first and foremost here to make sure that you can get some of those nice little machines that are standing over here, and that I'm going to show you a little later. And then I'm going to spend the rest of my presentation walking you through what freeform injection molding actually allows you to do. The first and most obvious case is, of course, to achieve a much higher speed of design. We can usually shave about 10 times of the time taken to do first components that are injection molded, and we can usually get you at least 10 times cost depression to get to those first components. That's, of course, important in the development phase, but it's also important if you're faced with a worldwide epidemic and needs the tools to be able to manufacture parts quickly. The second case is a case about making batch of one injection molding. Those three parts here were part of a little marketing gimmick that we did, but they might just as well be personalized injection molded items that were not just made for the show of it. That's one of the key benefits of injection molding with freeform injection molding. You get to actually personalize your components. The third case is spare parts on demands. I was mentioning it earlier, but it bears repeating. Having access to the materials that were used for original components is one of the key benefits of freeform. And if you combine it with nice little pattern recognition software from the company Adidas, you get a very nice, very easy to use identification of parts that can then be manufactured on demand. We have a lot to do with the medical device industry at Additive. We've spent significant resources qualifying the process for medical device development, and we've been involved in several medical device development projects to date. One of the key benefits of freeform injection molding is that if you use freeform injection molding with a material that is biocompatible when you start, you will usually also be able to make parts that are biocompatible after having been processed with our technology. And this may, for instance, be implant-grade materials that are implanted in sheep, for instance, if you want to test them in real life.
These titanium screws have been overmolded with a silicone by Teknologisk Institut. And Teknologisk Institut has actually demonstrated that these implants can stay for 3 months in sheep without really impacting the well-being of these sheep. Additive is very engaged and committed to being one of those forces that try to bring sustainable materials into the development tool chain. And one of the key challenges facing materials manufacturers catering to developers is they will either have to turn the materials into additively manufactured materials, or they will have to persuade product developers to start using injection mold machines in the development phase. We make that infinitely easier with Additive, since we have the opportunity to use the standard injection moldable granulates for the prototyping. Versatility is one of the other keywords that we use about freeform injection molding. Versatility means you can process the widest possible range of materials, means you can process the widest possible range of geometries. We've been into soft rubbers, we've been into metals, we've been into ceramics, we've been into highly reinforced plastics, all on the same platform, based on the fact that it's actually the injection molding that determines what kind of material you get out of your process. One of those examples is an extremely high performance material from Mitsubishi. When we talk about the weight to load bearing capacity, this material in a setting where you have about 70 grams of materials will allow you to carry more than 2 tons. We haven't done the calculations, but that seems to be a pretty high weight to load carrying capacity. And then we were talking before about conductive 3D printed components. This is another way of doing it. If you have a specialized polymer, which is also provided by our friends from Mitsubishi, you have the opportunity to laser structure and then subsequently plate components with conductive tracks, like on this antenna. And in that case, you can combine high performance materials with conductivity. A new concept that we have begun exploring is the combination of conventional metal tooling with 3D printed sacrificial inserts. The reason why this is an attractive concept for us is that we can combine pretty large injection molds with very small, intricate 3D printed structures that allow you to handle a lot of the complexity you would otherwise have to handle with movable sliders or collapsible cores or the like. So we can move from concept to commercialization to high scale with a high level of repeatable use from the metal cavity, combined with a very high design freedom from the printed inserts. This we've also used to create insert molded parts. For instance, this bracket, which is used by an automotive manufacturer. We combine metal threaded bushings with a high performance PPA to create a part that is actually usable in an automotive setting. And as another cute little example we've done lately, we've tried overmolding cables, basically the same process that we use for everything else. In this case, we had the cable running through the printed inserts, and we created a couple of cavities surrounding the inserts to quite simply overmold the cable. Very nice, handy little process. And lately, we have also been moving into the concept of live hinges, film hinges. Those are reputably difficult to do with 3D printing, but it's a native characteristic of the polypropylene material that we have been molding. And by combining injection molding with 3D printing, we have the opportunity of doing something that actually goes flip when you ask it to. One thing that is very recent with Additive is the concept of micro-injection molding. We used to be on a level of 50 micron with our resolution, but we are right now in the final stage of testing a setup that allows us to do 10 micron 3D printing. 10 micron means you're manufacturing voxels that are roughly the size of a white blood cell. So the building blocks we can create, the injection mold inserts we can create with a 10 micron optic allows us to step into the domain of micro-injection molding. As you can see, some of those parts that are shown on the screen here are extremely intricate. They're also very, very small. And this is just the latest bricks that we are laying on top of what is already a very versatile technology. We believe it to be one of the best research engines for materials manufacturers, for application manufacturers that want to be able to push the envelope on what they can do with their materials and their components. And that was basically what I had to show today. I know it was a lot of information, but please feel free to reach out to me, Adifab, anybody you know who has anything to do with freeform injection molding.
Thank you. Lasse, would you like the questions now?
Well, I actually think it might make sense to do the guided tour because I have an injection molder sitting in the next room, and that injection molder does not really like to be kept waiting because then things start going stale. So what we have here next to me right now is a 3D printer. It's to some extent similar to the 3D printers you would normally see sitting on the desk, but this one is built for industrial manufacturing. So it's featuring a backbone, which is a 40mm steel plate. We use some of the highest order electronics you can buy on the market. We have our own build system and automated resin supply. And the main reason we combine all these features is we want to be producing something that is actually usable in an industrial manufacturing setting. So when we look at what is going on inside this machine, you can come a little closer, Marcel. We have the lid, of course. Then we have a build plane, which is lowered into the build vat. The build vat contains the magical sauce that is Adifab's key invention. And what you have underneath here is a pre-baked component that we made just. Can you see? I just want to make sure that the video is actually running.
It is running. Just don't look at Lasse, look at Marcel.
Okay. Yeah. Look at Marcel. Well, that is definitely interesting. Marcel, did you?
Screen sharing from the other computer because we only see the little image.
Okay.
Yeah, I will just unshare your screen. Here we go. This should be better. Sorry about that.
Thank you. So I'm just pointing at the build plane, which contains, in this case, a 10-micron printed object. I'm going to be moving with this 3D printed object from the printer, which I just explained, and I won't repeat myself. So anybody wanting to have a look, feel free to reach out. We do guided tours, most of them virtual these days, but once in a while we actually also open the doors to visitors. So this is a 3D printed part, or a 3D printed injection mold that will eventually turn into a part. And now I'm going to move from the printer into the second phase of the operation. We, of course, need at this stage to remove the printed part from the build plane. And that happens basically here. I can do it, but I won't be able to move all the steps through with you guys. So now this part is actually ready for cleaning. Cleaning takes place in this station here, beautiful little machine. Everything we do is based on the same basic footprint. We've developed our own lab bench because we want to be absolutely ensure that we can provide a ventilated enclosure that allows operators to operate machinery safely and efficiently without having to concern themselves with spilling stuff on the table or evacuating stuff from tanks or whatever. We've tried to ensure that, for instance, this cleaning station is fully ATEX approvable so that we have the opportunity of supporting regulatory requirements in whatever market we are actually working. So after the cleaning process, which takes about 20 minutes for a typical batch of components, we move into the post-curing. Post-curing is a standard process. It happens over here. We use these little UV curing ovens from a dental company in Europe. And what you get out of the post-curing are printed tools. So these printed tools, we are now going to be filling. Sorry to be moving around, but it's part of the job myself. So now we move from the 3D printing showroom into the injection molding lab. I have prepared an injection molding machine, but I don't know if it fell asleep while I was talking. I hope everybody else is still awake. So this is one of those little machines that we have been using at trade shows quite a few times. It's a baby plast. And what we do, if you come a little closer myself, is to insert this printed tool into this very simple cavity here. I have to close the lid, otherwise the machine won't go. And then what I do is simply to press go, and the machine goes. Now it's injecting material into the printed tool, and we'll have to wait about 30 seconds for the material to cool, because we want it to be only lukewarm when it comes out of the machine. So in a very little while, now, what we have here is now a printed tool cavity with some polypropylene inside. As you can probably imagine, it's going to be pretty tricky to get this geometry out of the printed tool. So we will have to do something which is one of those particularities of the additive technology. We'll have to dissolve the tool. Before we leave this beautiful injection molding laboratory, I just want you to have a quick look at what else we have on the floor. We've tried to see how big we can go. And so far we are at about 20 centimeters component length. But some of the experiments that we are running with injection molders involving combinations of metal inserts, watch the stairs, Marcel, and 3D printed inserts. So now we move to the last stage of the process. We're now back in the printer lab. Marcel is through the door. I'm not going to be messing around with parts that go into the demolding tank, because the stuff in there will make this printed tool go away. But this is actually what allows us to make an intricate component like the one I showed in the little bit video a couple of, I think it was a month ago. Thank you for the opportunity, Morten. And this is what brings us into the component domain. In this case, a pretty intricate lattice, but it might also be a standard industrial injection molded component in a given material. On the first floor of Additive, we have office space. We have a machine building department somewhere over here. And in a couple of months, we will have to relocate because we've basically grown out of these premises. But in the meantime, we are here. We are definitely willing to collaborate and have a look at your particular talents. So I hope to be hearing from a lot of you after this session. And now, that's a good time for questions.
Great, thank you for that. So first we have a question from Heinz. Heinz, please go ahead.
Hi, can you hear me?
Yes.
I hear you loud and clear.
Good. My name is Heinz Neumann. I'm from the company called PowerMech. We are, motor guys. How does one get started with the freeform injection molding?
Well, as a matter of fact, there is one key number to remember, and that's the phone number of Additive. We have two opportunities to offer, basically. We can sell you machines. Alternatively, we can help you find some of the customers, Krebs & Co, Da Vinci, other guys. Well, Skive has also onboarded with tool making education. So it pretty much depends on what you need. But if you want parts, Krebs, Da Vinci. If you want education, Skive, Værktøjsmauddannelse. If you want machines, please call me. I don't know if that answered the question.
It looks like it. Yeah, thank you. So we have another question from Carsten. Carsten, please go ahead. If you would start your video as well. Thank you.
Hello, can you hear me?
Hey, Carsten, good to see you again.
Yeah, hello, Lasse. And thank you for a very good presentation. I just have a little question for you. Can you tell us a little bit about what is the limitations with freeform injection molding?
Yeah, I can share a bit. We of course hard at work trying to minimize those limitations, but you as a first mover had some of the experience. It's pretty difficult and pretty time consuming and pretty expensive to do very large parts. So I wouldn't expect any of our customers to start printing stuff this big as molds. We're trying to circumvent those limitations by combining metal tooling with printed inserts, and that seems to be one way to go. And then we have a few limitations in terms of materials that we can process. We are mostly compatible with injection molding polymers, but the challenge we occasionally face is that materials may be sensitive to the alkaline solvents we use for the demolding. In that case, we can do two-part tooling as well as anybody else. But the problem we will face will then be that the components will have a tendency to dissolve along with the mold, and that's not really practical. But apart from that, I think the major limitation we face is that of size, and that is one where we will have to find individual solutions.
Okay, we have one more question from Said. Said, please go ahead.
Yeah, thank you very much, Lasse, for the presentation. One of the questions that I was asked, it was about recyclable material. Can you elaborate more about which materials, recyclable materials, you are dealing with now?
Well, we've actually been covering a lot of ground lately. We started out with the PP polypropylenes from the company Plastics in Lemvig, and did a couple of very nice projects with these guys. Then we realized that Denmark is actually home to quite a few very, very high-end recyclers of material. So we started collaborating with Rematch and O. Vestergaard Larsen, and then we got some contacts from Finland, a company that is combining polypropylene with cellulose from the paper manufacturing. We got into dialogues with a guy in UK who is doing recycling of nylon fishnets. Did some buttons for a shirt with him and a design student. So I think what we are trying to help people realize is that recycled biomaterials may not be as difficult to integrate in the product development as they used to be. Most materials manufacturers make initially materials for injection molding because that's where the high volumes are. And by enabling them to bring their injection molding grades into the prototyping domain without having to make specialized materials, we are helping these product developers and these materials manufacturers to actually test out the validity of recycled materials. And in many cases, validity is actually pretty high.
Yeah, and I expect that in the near future, food grade material will be a high focused recyclable food grade material. Because if you go to the supermarket, you can see some product which has been packaged, and then you can see it is written 100% recycled. And I think is that correct? Is it the way? I mean, is it what is happening now?
I think it's a very good point. And what we are seeing is that the packaging industry is increasingly trying to think in terms of circular economies. On the home market, we've seen Rema 1000 take important steps in that direction. We've been working with several hard packaging manufacturers to make lids that incorporate the standard functionality of flip caps, for instance, but based on recycled materials. And these efforts seem to be paying off in the sense that some of the larger hard packaging manufacturers in the world are actually looking into recycled materials because they can now be processed in a format similar to their high volume manufacturing.
Yeah. Thank you very much, Lasse.
Thanks a lot.
Yeah. And there are no more questions.
Wow. So I guess I actually managed to wrap up this ahead of time.
It seems so.
You did, Lasse.
So, yeah.
I talk almost as quickly as you do, Morten.
I would just say, you know, everybody out there, give Lasse the thumbs up and all the emojis. Lasse, you did perfect, and you have actually been a pioneer in this cyber physical concept, because you have just provided the first actual company visit that we have done, you know, on the fly, on the remote, which means that you have had probably the first, you're probably one of the first companies in Denmark that have done a company visit to people that are all over the country, but also internationally. So congratulations on that, Les.
Wow.
I cannot stress my appreciation enough. We just have a little bit more time. I want to stress a few points. When you do webinars, which is you know, the online events where you don't have physical participation, I have a rule of thumb that if you have the number of registrants for the events will usually turn out to be half the participants. And then when the event ends, you will have only 25% left. But we are still approximately 90 people here. So we are actually, we're just scraping a little bit under half. So I think that is just, I'm not allowed to swears, but that's really awesome. I would just like Sarah to do, because you know what is really important to us is of course your opinion, and after this you will get an email requesting you for some feedback, and you don't have to give us feedback on the flickering screen and the sound for Roberto. We are of course aware of that. We would rather have feedback on the more intricate parts about how to improve the concept itself. I mean, there are some technical issues that we will be working on, and of course they will be even better next time. So give us constructive feedback on the things that really matters. And feedback you can give us already now. And I don't know, Sarah, if you can have a poll ready. And that will be a question for everybody. And you can just pop it up now. Is it on? And that is the question, which presentation did you find most interesting today? And you will just actually choose one, and then you will just submit it, and we will be able to give you the answer in just, let's give you 15 seconds or half a minute to answer while I'm talking. When I'm finished here, what we will do is that we will try to give you a little bit of online networking. We know this is hard, but we will do it anyway. When I'm finished with my monologue here, I will ask the ones that do not want to do online networking to log off. And after that, we will do what is called breakout sessions, breakout rooms, where we will put you in rooms approximately 4 people, and you will introduce yourself to each other. And you will also discuss which presentation you thought was the most interesting today. And we will give you 15 minutes to do that. And then we will meet again in the main room. And if there's if people want to, we will do an additional breakout room. So those of you who would like to to do the online networking session, please stay with us when I'm finished here. Should we close the poll now and see the results, Sarah? We will just close the poll, and I think we will get a result real soon. I'm just looking into my phones. And okay, so it looks like Adifab is taking home the main part here. Actually, 44% combined. Other than that, it looks like Roberto has not been punished, because we, as technical crew, had some issues. So that is really nice. Christian Slette is at 4%, and there was a really valid question there, why we were not in the field actually seeing this work, and that was going to be our surprise today, that we would actually go to Køge and see them print 3D concrete towers, and that wasn't possible due to the situation. But I think this gives us something to work with. I really do appreciate everybody's poll results. As I said, the next Curious Today Partner Tomorrow event will be on the 21st of April, and that will be starting again at 3:30 with the technical introduction, and we will move on from 4 p.m. and it will be right after what we call Praktik or Project Day, which is where the companies meet here at SDU and tell our students how the students can get knowledge from the companies. And we basically see Curious Today Partner Tomorrow as a courtesy to the companies, where we actually spend time afterwards on telling the companies how can they actually get top quality research knowledge from us to and into their companies. And again, it's called Curious Today Partner Tomorrow. We don't see anybody being our partners specifically, tomorrow, the 28th of August, but please do feel free to reach out. We also have a chat that we will go through, and there will of course be a follow-up email from me, and I will give you the dates of the upcoming events, and the teaser videos that the researchers have made and that Les have made will be on the website sdu.dk/curious, as long as also with the video that we are doing here today. I don't know, Sarah, do we have Susanne's feed still? Can we see if they have fallen asleep in Aarhus? Just to have a quick look at what's going on up there. Could we highlight the video? They are there. They are still there. And I can see, Eva is there. Hi, Eva. Can you wave at me? There she is. I hear that you brought no computer and you brought a phone with no power on. And were you there on time? Oh, and they are ready for the beers. Could we just wait to Aarhus and say thank you for your participation? And I don't know if they are still if there's still some left in Sønderborg, or they have gone home already. I don't know. Frederik is there. You want to say?
Whoa, just a second. We are here. Vi prøvede at lave en skrue, men det virkelig.
We are here in Sønderborg, but thanks.
Thanks a lot.
We are about to leave. We're not so many, but thanks.
We are doing our networking now.
Networking is going on behind me.
Yes, network.
Thanks.
I simply love to see this because this is what the distributed, not just the cyber-physical, but the distributed cyber-physical of it is all about. Is people being together in smaller groups, beating the social stress of not being able to meet so many people, but still do some networking with like-minded people. I really do appreciate that. I think I'm going to wrap it up here and give those who do not want to do online networking just 1 or 2 minutes to log off, and then we will do the breakout rooms. If there's none left, it's fine. Then we will go home for today. Otherwise, we will see some of you again already next week. And otherwise, I hope that you will get in touch with us. I'll make sure that you get the phone number for Søren Elmer, who's our contact point, and it can, of course, be research projects, it can be consultancy, and it can also be student activities. So please do not hesitate. Now you know a little bit about what we can do in additive manufacturing, and when you join us again on the 21st of April next year, you will know also how strong we are in simulation. And also, please do not hesitate to propose subjects for us. We will be very happy to address them in the future. We will have Curious Today, Partner Tomorrow every 6 months. And basically, that's it from me. Thank you for participating.